So, welcome to Pure 2, Chapter 9, Differentiation. This is the first twin of the evil twin. We got the differentiation and the integration, okay? And I can fairly say differentiation is the lesser evil. And integration is the bigger evil. It's like always in a pair of siblings, one is less evil and the other is more evil. Which one you're in, I don't know. But anyway, so evil twin. So differentiation. So I'm going to do a quick breakdown on the topics on chapter 9. So if you know my notes, they're not as thick. You probably haven't seen as thick as this one. There's up to page 31. So, but if you can imagine, this is the lesser evil. Think about integration. We'll worry about that later. So chapter 9, differentiation. You're going to learn quite a lot of differentiation skills. 9.1, 9.2 is about basic knowledge about something you have to remember, like some key facts for different derivatives you have to remember. For example, how to differentiate sinx and cosx and how to differentiate exponentials. That's something you have to remember how it differentiate. It's like when you ask you how to differentiate 2x squared, you'll know multiply by the power of power minus 1. So that's something in your mind you will be remembering. 9.3, 4, and 5 are the trios, the three rules that rule, pun intended, all differentiation. So 3 rules that rule the differentiation. You're going to use the majority is either one of these 3 that you'll be constantly using: chain, product, and quotient. And then 9.6 is where we differentiate more trig functions, but we have to use these 9.3, 9.4, 9.5 to help us. And then parametric differentiation and implicit differentiation, new stuff. So 9.1 to 9.8 are differentiation skills. Right? Next, 9.9 is where you use second derivative, another layer of second derivative. In year 1, you would have learned to use second derivative in proving if a stationary point is maximum minimum, but there'll be a little bit more in 9.9. Okay, another definition using second derivative. 9.10, part 1, part 2 is about rate of change, but modeling, which will link into integration as well. So that is the end of the breaking down of the chapter. That's not the end of the lesson. That's the end of breaking down. By the end of the whole 9.10 part 2, maybe I would suggest you go on the next page and write a summary of what you've done in here. It's quite full on. Right, so let's dive in. 9.1. Okay, the first lesson about differentiation is sinx and cosx. So I said recall, but actually I just realized you haven't learned it. So, call it notes, whatever. The derivative of sinx is cosx. That's a fact. Okay, so that's how you remember it. The derivative of sinx is cosx. Well, why? You will learn the proof about using first principle later. But for now, you have to remember derivative of sinx is cosx, and the derivative of cosx is negative sinx. One thing you can remember is using what I call a sinx cosx clock. So if you have sinx, in here sinx, cosx, negative sinx, negative cosx. Then if you remember clockwise direction would be differentiation. So derivative of sinx is cosx. Derivative of cosx is negative sinx. Derivative negative sinx is negative cosx. So to set up this clock, you do sine, cos, and then negative sine, negative cos. Okay, so that's differentiation. That's how I remember it. Okay. You will also have learned this from chapter 5 about small angle approximation. If theta is a very, very, very small value, then the sine theta will tend to be the value of theta itself, and cos theta will roughly equal to 1 minus theta squared over 2. We always use radians when differentiating trig functions. Well, why? Okay, so you don't have to remember any of these, but it's good to understand what's going on. Right, so y equals sin x. So now let's say, okay, we use y equals sin x. Now, when we differentiate, okay, d by dx, or differentiate sin x, that's cos x. But do you remember what's the purpose of differentiating on the graph? The derivative means the gradient. So this line means the gradient of sin x is cos x. Now, when x equals 0, so when we do x equals 0, okay, then sine 0 will equals to 1. Sine 0 equals Is it sorry, sine 0, sorry, hang on. When x equals 0, so when x equals 0, so when x equals 0, cos x equals to cos 0, which is 1. Sorry, cos 0 is not 1. Sorry, cos sine 0 is 0. Cos 0 is 1. What it means is at the point x equals 0, the gradient of sine x is 1, right? Because the gradient of sine x is cos x. So at x equals 0, we know cos 0 is 1. So the gradient of sine x is 1, the gradient of it. Now, if we compare the graph left-hand side, right-hand side here, this graph is a radian, and this graph is in degrees. Well, might be asking, sir, why is degrees not 1, 2, 3, 4, 5? Because degrees is out of 360 degree. So if you think of 1 degree, it's the same as 1 over 360, and that's why it's a very small decimal. So 180 will be 0.5. That's where 180 degrees. So degree is divided by 360. Degree is always over 360. So in radian, now if you look at this graph in radians, you would see at x equals 0, the gradient is a perfect line of 1. 1, 1, and minus 1, 1 means the gradient of this line is 1, and that works. However, when x equals 0, you can see this tangent line, the gradient is not 1. If the gradient is 1, you should see a line like this, the tangent, but it's not. So that's 4. Therefore, that's why we use the radian, okay, in differentiating trigonometry. Right, next. Now I'm going to skip this for now. The first principle will save the best for the last. So come back to it later. We'll learn the application side of things first. So you've learned derivative of sine x equals cos x. Learn one more. Derivative of sine kx equals k cos kx. Derivative of cos kx equals negative k sine kx. Well, we know differentiating cos is negative sine. If there's a k, if it's a cos 2x, it'll be negative 2 sine 2x. Okay, so right, example. Find dy by dx. By the way, none of these are given in formula booklet, so you have to remember by heart, off by heart. Example. Find dy by dx given that y equals sine 2x. So y equals sine 2x. So sine kx. So the derivative, now left-hand side, is now y dy by dx. It was a y, but when we differentiate, the left-hand side becomes dy by dx. Now, I do stress the writing at the left-hand side because the left-hand side is like the name of the line you're working out. For example, when we're told y equals sine 2x, that means this line helps you work out the value of y. So y equals the name of this line. Okay, the purpose of this line is work out y equal. And the purpose when you differentiate is this becomes work out the gradient. So when you have to work out gradient, you should look for dy by dx. So dy by dx equals differentiate sine kx. K, so 2 cos kx 2x. 2 cos 2x. That's all. Okay. B, differentiating left-hand side, so dy by dx equal differentiate cos kx is negative 5 sine 5x. C, we have a plus in the middle, so we can differentiate 1 by 1. Is that when I ask you to differentiate, let's say, okay, so quickly, if I ask you to differentiate this, you will get dy by dx equals differentiate 5x squared is 5 times differentiate x squared is 2x plus differentiate 3x is 3. So that's 10x plus 3. What I'm trying to show you is when there's a plus and minus, that means we can differentiate separately, 1 by 1. So differentiate the first one. 3 cos x of dy by dx, left-hand side, right-hand side. Differentiate 3 cos x. 3 is a coefficient, so we're not going to do anything about it. Cos x, differentiating cos x is negative sine x. Now note, this is not cos 3x. This is 3 cos x. This is different to cos 3x. Okay. Next one, 2 sine 4x is the 2 is a coefficient, so we'll put a 2, okay, times differentiate sine 4x. Okay, sine 4x is 4 cos 4x. So now we can simplify it. 3 times negative sine x is negative 3 sine x. 2 times 4 cos 4x is 8 cos 4x. 2 times 4 is 8. The 2 does not multiply to the 4x because you don't multiply the scale factor or number and multiply a scalar into the degree. Left-hand side, dy by dx. And that's the answer. Okay. If you're happy with it, then have a go at this practice question. Okay. Pause the video, have a go at the question. When you're ready for the answer, you can press play. Here are the answers. Okay, so broken down the steps. Differentiating 3 sine 5x is 3 times differentiate sine 5x is 5 cos 5x. So the answer is 15 cos 5x. Part B, 4 cos 3x, differentiating, so 4 is outside. Cos 3x is negative 3 sine 3x, so negative 12 sine 3x, etc. So I'll let you read. If you got anything wrong, if you don't understand, do ask me in the lesson. So, right. Then one more before we go back to the first derivative. First principle. Example. A curve has equation y equals a half x minus cos 2x. Find the stationary points. So when you see the word stationary points, by now, the first thing that should come to your mind is dy by dx equals 0. Right? dy by dx equals 0. On the curve in the internal, in the interval where x is between 0 and pi. So dy by dx equals 0. So first of all, we have to work out what differentiate. So we're told y equals a half x minus cos 2x. Let's differentiate. So dy by dx equal differentiating half x is a half. So it's a minus and a minus. Okay, so minus. Differentiating cos 2x. Cos 2x is differentiating cos 2x is negative 2 sine 2x. So minus makes a plus. So a half plus 2 sine 2x. Right. So I do it step by step. Differentiate half x is a half. That's a minus, so I rewrite the minus. I ignore the minus when I differentiate. Then when I differentiate cos 2x on its own is negative 2 sine 2x. I realize the minus makes me a positive. That's a plus. I was told that equals 0, so I'll make it equal 0. So then this becomes just a cast diagram question to work out the value of x. You can pause the video and have a go, full go at the question, and let's see if you got it right. Okay. But if you want me to go through it, I will do it now. So I bring the half over, it'll be 2 sine 2x equals minus a half. Divide 2 over, so sine 2x equals negative a quarter. And then I need to do inverse sine. So inverse sine, so arc sine of negative a quarter. So I put in a calculator, negative a quarter. I get, inverse sine of negative a quarter. I get negative 0.2526. So negative 0.2526 is here. 2527. I need sine to be negative, so the other answer will be here. 0.2527. So to work at the first value, I'll go in a positive angle direction again. So the values are 2x equals, so pi plus 0.2527. And the answer, the other value is 2 pi minus 0.2527. Now, by now, you shouldn't be struggling with cast diagram. If you do, go back to Pure 1, chapter 10.5. Okay, if you do need more work on cast diagram. So then you put in calculator, you should get x equals, so add them up and divide by 2, 1.70. I did 3SF or 3.02. But that's not the coordinates because coordinates need the y value as well. So stationary points means a coordinates, a pair of coordinates. So I find a y value. To find a y value, I need an equation of a y. So equation of y is the original. Okay, it's not this one because there's a dy by dx. Right, so just to make sure you don't put in the wrong equation, you are working at y value, so you put in a y equation. So y equals a half x minus cos 2x. So y equals a half x minus cos 2x. Plug in the calculator, make sure you calculate in radians, and you should get y equals to 1.82 and y equals 0.539. So therefore, the stationary points are 1.7, 1.82, and 3.02 and 0.539. And that's the end of the question. The end of lesson? Nope. Because we have to enjoy our desserts with first principles. Right. So you will also have to use the first principle to prove derivative of sin x equals cos x. Now, this is examinable and it has come up in exam before. The other version of this is to prove the derivative of cos x equal negative sin x. So I'm going to show you how to do this. Okay. First of all, hopefully you do recall first principle. So first principle is another way of differentiation, is the grandma of the derivative of grandpa. Okay, is the ancestor of it. Because the shortcut you've learned, for example, differentiating 2x squared, if I ask you to differentiate 2x squared, you get 4x. This is actually the product from the answer from the shortcut from the first principle. Okay, it's like everything you enjoy now is the stories about why your ancestors are, they are doing things, and that's why you're enjoying life right now. The trees that you are, what I'm trying to say. Anyway, whatever. You understand what I mean? But basically, ancestors give you everything that you have now. That's what older people would say. So we're gonna learn try to learn the grandma of differentiation. So f dash x. So is f of, oh wait, hang on, I forgot. They have the limits. So limit h tends to 0, f of x plus h minus f of x over h. The way, if you learn it my way, the way I set up is set up as f of x and f of x plus h first. F of x is sine x. F of x plus h is sine x plus h. Right? So f of x sine x, f of x plus h, therefore you replace x plus h into x. So sine x plus h. I will then sine of x plus h, sine a plus b, use your compound angle formula, sine a cos b plus sine b cos a. Next, I can use the formula. So I'm going to rewrite that. So f dash x equal limit h tends to be 0. Numerator is f of x plus h. That is sine x cos h plus sine h cos x minus f of x over h. I'm going to color code it for you. This part is the f of x plus h, and sine x is f of x. So I'm using a formula. So the good thing about setting up this way, a bit more structurally, that helps you do things one by one. Here, you can actually expand a bracket really nicely first before you put it all together. Is that when you do cooking, you do one thing, you prepare one thing first, you prepare the onion first, make you cry, and then you prepare something else, and then ultimately you put them together, frying pan. So do the same. So that's what we're trying to do in here. Okay. Now the next step. Now the second line of the equation to give you a bit of hints how to do it. We are told sine h over h tends to 1. Now where did that come from? That comes from small angle approximation. As h tends to 0 or theta tends to 0, small angle, sine theta is the same as theta. So imagine that if that's a theta, as theta tends to 0, sine theta will become theta. So the top will become h over h is therefore 1. And that's where this comes from. You don't have to prove that. So you're told sine h over h tends to 1. So we're trying to make this happen. We'll try to make a sine h over h. So we look at the whole thing. This term is sine h. That means this one will form on its own. Cos h minus 1 over h. So we need a cos h. This one is cos h. What about sine x? Now sine x has sine x. So we'll put these two together. So what I'm going to do is I'm going to rearrange these two terms. So I can put the sine x cos h with the minus sine x together. So limit h tends to 0, sine x cos h minus sine x plus sine h cos x over h. Next, the first two terms both have sine x, so I can factorize a sine x out. So then it becomes cos h minus 1, and that's where cos h minus 1 comes from, plus sine h cos x over h. Next, I'm going to split the fraction. So sine x times cos h minus 1 over h plus sine h cos x over h. Now then, that's my cos h minus 1 over h, and that's my sine h over h. From the question, I was told this equals 0, and this equals 1. So that's what I was told from the question. Therefore, I rewrite that limit h tends to 0, sine x times 0 plus 1 times cos x. We know sin x times 0 is 0. So limit h tends to 0. 1 times cos x is cos x. And we write left hand side. Now the limit actually does nothing in here because there's no more h. The limit tells you to replace h is 0. But if the expression is no h, then there's no point for the limit, right? So then you can rewrite f dash x equals cos x. And that's the 4 marks for the question. That's a 5-mark question usually. Right. So what I want you to do is I want you to read it again. Okay. So I want you to write down step by step in between what have I done in here. Or, you know, it's just for your own good, because when you reread the notes, if you maybe in a few months' time, if you try to read it again, you probably forgot what to do. So these little steps are to help you catch up with step by step and try to remember why do we do it. Okay. And yeah, because it's impossible to remember term by term. So in exam, what you can only do is in maths is try to remember why do we do that? What makes us to do the next step? Okay, so why and what? If you're happy with it, okay, after you understand the whole thing, then can I invite you to try this question? It's exactly the same question I've told you is an exam question, exact same way. Try to have a go at the question. Now, I'm not going to go through this because you've got the answer from the previous example. But I would suggest you not to read it. Try to learn, understand it, and then replicate it. Okay, if you really struggle, then have a look again, have a peek, just a sneak peek. Okay, but if you want a bit of a challenge as well, then once you finish this practice, do the cos x as minus sin x as well. Right, and that's the end of this question of this lesson.